Chapter 1, Sequences and Series, Section 1.3, Geometric Sequences. This is Mr. Jones. Mr. Jones is holding a meter stick and a tennis ball, and he is going to assist us today by bouncing the tennis ball. Mr. Jones?
Okay, whenever you like.
Thank you, Mr. Jones. Your check will be in the mail. The bouncing ball demonstrates another kind of sequence. If we made a list of the height that the ball bounces back up to, starting from its initial height, you'll notice that the difference between the terms is not a constant amount, so this is not going to be an arithmetic sequence. If the conditions in this experiment were perfect, we would actually see that the ball bounces back consistently to a specific percentage of the height from which it fell. For instance, a ball dropped from a height of 1 meter might bounce back to 80% of its original height. This would form the following sequence in centimeters. 100, it would bounce back up to 80 centimeters, bounce back up to 64 centimeters, bounce back up to 51.2 centimeters, and back up to 40.96 centimeters. To get each successive term, we aren't adding or subtracting, but instead we're multiplying by a factor of 0.8, or 80%. And this is called a geometric sequence. A geometric sequence is a sequence in which the ratio between consecutive terms is constant. In an arithmetic sequence, we're adding a constant difference between the terms. In a geometric sequence, we're multiplying or dividing by the same number to get from one term to the next. And that number that we're going to multiply by is the constant ratio. We're going to call it R. Therefore, the terms of a geometric sequence will appear as T1 times R, T1 times R multiplied by another R, so simply T1 R squared, T1 R cubed, and so on, all the way out to the nth term, which will equal T1 times R to the n minus 1, giving us the formula for the general term of a geometric sequence. Tn equals T1 times R to the power of n minus 1, where again, n is the term number, T1 is the value of the first term, and R is the ratio between the terms. To find the ratio between the terms, what you do is simply take any term and divide it by the preceding term. If you go back to the bouncing ball example, you'll see that taking any term and dividing it by the previous one will always give an answer of 0.8. 80 divided by 100, 64 divided by 80, and so on. 20 bacteria cells present in the refrigerator, and every day the number of bacteria cells double. So it'll be 20, 40, 80, and so on. Assuming this rate of growth can continue, how many cells will there be after 2 weeks? This is a geometric growth. This is multiplying by 2 every single day. So let's look at the general term for a geometric sequence. Tn equals T1 times R to the n minus 1. We know that T1, the initial amount, is 20. We know that the rate of growth is doubling, so it's multiplying by 2 to go from one day to the next. And we're looking for the specific situation where n is 14. We want the number of cells at the end of a 2-week period. So we're looking for T14, which will be 20 times 2 to the power of 14 minus 1. 14 minus 1, of course, 13. 20 times 2 to the power of 13. Make sure you type this properly in your calculator. You will get 163,840 cells of this particular bacteria at the end of the 2-week period. The second term of a geometric sequence is 20, 48. The fifth term is negative 32. We need to determine the values of T1 and R. We need to give the general term, Tn, and then list the first 3 terms of the sequence. Well, I kind of like a hands-on approach here. So what I'm going to start with is just to kind of look at what does this sequence look like. We've got a first term, we don't know it. We have a second term, 2048. We've got a third term, a fourth term, a fifth term, which is negative 32. Now, since I know that this is a geometric sequence, I know that to get from one term to the next, I'm always multiplying by r. So to get from 2048 to the third term, I'd be multiplying by r. To get from 2048 to the fourth term, I'd be multiplying by another r, so in other words by r squared. And therefore to get from 2048 to negative 32, I must be multiplying by r cubed. This means that negative 32 is equal to 2048 r cubed. Solving for r, we divide both sides by 2048. We get r cubed is negative 32 over 2048. I'm a big fan of reducing fractions. This reduces down to negative 1 over 64. Isolating r, we cube root both sides. The cube root of negative 1 is negative 1. The cube root of 64 is 4. We've got our value for r. r is negative 1/4. So we've solved the first bit, determine the value of r. Now we want to get t1. Well, to go forward from 2048, you multiply by r. Therefore, to go backwards from 2048, we're going to divide by r. 2048 divided by negative 1/4. In other words, 2048 times negative 4. And if you grab your calculator, you should get negative 8,192. This means we can now give the general term. The general term, Tn, is the first term, negative 8,192, times r, negative 1 over 4, to the power of n minus 1. And giving the first three terms of the sequence, we have negative 8,192, which we've calculated. We have positive 2,048, which was given. And again, multiplying by negative 1/4, we get negative 512. Something to notice on this sequence, since the ratio was a negative number, you'll note that alternating terms of the sequence are positive and negative. Negative to start, positive, negative, positive, negative, positive. This will happen when your r value is negative. And finally, two questions for you to do on your own. For the geometric sequences given below, find the general term, Tn, and then calculate the value of T10. Calculate the 10th term. In the case of the second example, give it as a simplified fraction rather than a hideous, nasty decimal number. Have fun. See you in class.